All right, so 3.10 related rates. Probably one of the most interesting of the sections, but interesting also means a bit complicated. So what we have here is we want to see how one rate is affected through another by the formula they're connected to. So the first thing we're going to talk about is how pumping up a balloon. We know when pumping up a balloon that the radius is going to change. But we also know when we pump up a balloon, its volume is going to change. So essentially what we're going to ask is a particular question is how's the rate of change of the volume related to the rate of change of the radius. So when pumping a balloon, how does the rate of change for the volume relate to the rate of change for the radius? Okay, so what we know is, and maybe you don't know the formula right offhand, but you can always look it up, is we know that volume is related to the That's correct. Okay. Sure. That's fine. That sounds good to me. Yes. Excellent. Thank you. You too. Sorry, I'm still doing a video. All right, so crazy stuff happening right now. So so I want to know how the rate of change of the volume relates to the rate of change of the radius. So what we know is there is a volume equation. So I know that volume is equal to 4/3 pi r cubed. And you could look that up or just ask Google. So I want to know, this actually relates the volume directly to the radius, but I want to relate their rate of change. So what we're going to do is we're going to take the derivative of both sides with respect to time. So as something increases, I want to know over time, I want to know how the other one increases. So we're going to take the derivative of this expression with respect to t on both sides. So the derivative with respect to t, the derivative with respect to t of both sides. Okay, so make sure that we know that what are constants and what are variables. Well, technically, the volume is going to be changing over time, so v is technically a function of time. And also, r is going to be changing over time, so really r is a function of time as well. So we know implicitly when we take these derivatives, like the derivative of v with respect to t is just going to be 1, but every time you take the derivative of something that's not t, you have to follow it by dv dt. So this is going to be equal to dv dt. Now this is a constant, so you can pull out that constant and take the derivative with respect to t of this r cubed. Now remember, the derivative of r cubed would be 3r squared, but remember r is not t, so you have to follow it by dr dt. So this is going to be 4/3 pi times 3r squared dr dt. So this is going to simplify to 4 pi r squared dr dt. So that means the rate of change of the volume with respect to time is going to be 4 pi times r squared with respect to its rate of change. So these are the relations between the rates of change. No. Okay, so maybe a question that we would ask is, an example of this would be, what is the rate of change of the volume of a sphere when the radius is 6 meters and the radius is increasing at a rate of 2 meters per second. So what they're asking for is, what's the rate of change of the volume? What we know is dV dt is the rate of change of the volume. And they want to know when the radius is equal to 6, so r would be equal to 6, and the rate of change of the radius, this thing would be equal to 2. So our solution dV dt would be equal to 4 pi, now they said r is equal to 6, and then dr dt is going to be equal to 2. So 24 times 2, oh, it should be 6 squared. So this is going to be equal to 288 pi. Now, meters cubed per second, because of this is 2 meters per second, and this is 6 meters, so 6 meters squared. So this will be meters squared, and this is going to be meters per second. All right. Rising. So this is a hot air balloon rising straight up from a level field, is tracked by a rangefinder 500 feet from liftoff. At the moment, the rangefinder elevation, angle is pi over 4, so 45 degrees. The angle is increasing at a rate of 0.14 radians per minute. So everything's in radians, you can see now. How fast is the balloon rising? At that moment. Okay, so what you almost want to always do here is draw a picture. Now, I didn't draw a picture for the other one because the equation was direct. You just look at the equation for volume and how it relates to the radius. But in this case, we have to kind of build our equation. So what I know is that we have a hot air balloon lifting straight up. So here's our balloon, and we have a rangefinder that is 500 feet away. So I have a rangefinder that is 500 feet away. And what we are doing is we are tracking this balloon through that rangefinder. So things that we want to know is, I want to know what is changing. like what's a constant and what's not a constant. So since this balloon is going up, we can see that particular lines are changing. And this height is going to change as that balloon goes up, and this distance here is going to change as that balloon goes up. The question is, does this line change? If this balloon goes straight up, does that line change? Does that rangefinder move? The answer is no. So this is a constant, and these are not, right? So what I'm going to do is I'm going to label this y, and depending if they're asking, we might need this side too, but I don't think they're asking for that. What I know is I know that that theta, this is going to be equal to theta. Now, things that I am not going to label is I know that they said theta is equal to pi over 4, but I don't want to do that right now because those things as they sit are changing. So what I want to do is I want to relate these three things through a formula, and then I'll plug in the values after I find that relation formula. So make sure when this balloon rises, y is changing and theta is changing. So both those things are changing. So don't write pi over 4 right now because it's increasing. So let's find out an equation. So what equation or what trig function? So with this angle, this is the opposite side, and this is the adjacent side to that particular angle. And what we know is that the tangent function, I know the tangent of theta is going to be equal to opposite over adjacent. Now 500, I wrote 500 because that one is not changing. That actual distance is constant. So remember that this relates these variables directly together, but what I want to do is I want to relate the rate of changes. So what I'm going to do is I'm going to take the derivative with respect to t on both sides. So I'm going to take the derivative with respect to t of this tangent of theta, and I'm going to take the derivative with respect to t of this y over 500. Well, what's nice here is you could use the quotient rule if you want to, but knowing that the bottom is a constant, but it'd be easier if you just pull out that 1 over 500 and take the derivative with respect to t of y. Just a lot easier. But the quotient rule will get there too. Okay, the question is, what's the derivative of the tangent function? Well, the derivative of the tangent of theta is the secant squared of theta, but remember, this variable does not match this variable, so you have to multiply it by d theta dt. When you take the derivative of y, well, the derivative of y would just be 1. Again, this variable does not match this variable, so you also have to have dy dt. So dy dt. So this is a really good formula. Secant squared of theta, d theta dt is equal to that. Now after I've found the derivative, so derivative first, constants last, okay? Constants last, derivative first. The only reason I put the 500 in is because that is not changing, so that is a constant always. So, all right, so let's plug in our values. So I know that the angle is pi over 4, and where is our theta? Oh, theta's here.
I'm waving to my reflection.
Oh, I gotcha. So this is going to be equal to the secant squared of pi over 4, because that's what that is, times d theta dt. Well, the question is, it says how fast is the balloon rising at that moment? So I think they're asking for dy dt. So d theta dt is this change in angle, so this is going to be times 0.14 equals 1 over 500 times dy dt, which is the question they're asking. They're asking for dy dt. So multiply this by 500, so this is 500 secant squared pi over 4 times 0.14. And just be careful when you put these things in. The multiplications are there, is equal to dy dt. So plugging those things into my calculator. So when you do that into your calculator, you want to make sure that your mode is in radians. So second quit. So I'm going to go 500 secant squared. Remember, secant is 1 over the cosine squared. So this is going to be 1 divided by the cosine of pi over 4. Second pi divided by 4 squared. So that's your secant squared times 0.14. So what we get is, I get exactly 140. So that means this is equal to 140 feet per second. All right. Time for something similar to this, but a little more fun. Now, remember that this was asking about angles. That's why I was using trig functions, okay? If I was only talking about side links, then I'd be using the Pythagorean theorem. So we have to figure out what formula is going to relate these things. So here's the one I'm talking about. So highway chase. A police cruiser. So it takes forever to write these out. Approaching a right angle intersection from the north is chasing a car, speeding car, that has turned the corner. And is now moving straight east. Oh, when the cruiser is 0.6 miles north of the intersection, and the car is 0.8 miles to the east, the police determine with radar that the distance between them and the car is increasing by 20 miles per hour. If the cruiser is moving at 60 miles per hour, hands are falling off. At the instant of measurement, measurement, bless you, what is the speed of the car? Okay, so, whew, that's a big one. What we're going to do is we're going to draw some pictures. And all that information, unfortunately, was needed so we can nail this, the picture just right. So what we have is we have a car coming from the north and another car going east. So what we have our two cars. We're going to have our police car. Here's our police car. Maybe I have my pens. Can I have them? Oh, I guess it's green. There's the police car. And then we have the other car. So somewhere over here is the other car. So there's things that I know. Actually, what we want to do is before I put in the constants, before I do anything, I want to draw a picture and understand what's going on. Because I don't want to put numbers in yet because I need to know what things are moving. Because if you start putting numbers in now, you're going to put numbers in the equation, take the derivative, and everything's going to get messed up. So let's talk about the pieces that are moving. So what I know is I'm going to call this X, I'm going to call this one Y, and I'm going to call this one S, or D, whatever you want to call it. Now, if this police car is going this way, and this chase car is going this way. So this one's moving down, right? He's going down, and he's going away. What's moving? Is X moving? Is X changing? Well, yeah, if he's going this way, this is going to get bigger, right? Is Y changing? Yeah, if he's coming down, Y is going to get smaller. And also, if they're moving at different speeds, okay, even if they're moving at other speeds, this thing is clearly going to change. So all three of these pieces are changing as these cars are moving. So let's come up with a formula that relates these three variables together. Well, this is a triangle. It's a right angle triangle, so I know that x squared plus y squared is equal to s squared. A squared plus b squared equals c squared. So don't put any of the numbers in now because all these things are changing. So we need to know the rates of change if everything is changing. If you put them in now, you don't have the same thing. You'd have like say if you said x was constant, that means this car is not moving, so only the police car would be moving. So then the rate of changes would be quite different. So now what I'm going to do is I'm going to take the derivative with respect to t of this entire thing. So of this one, x squared plus y squared, and then the derivative with respect to t of s squared. So remember, none of these variables match t, so every time you take the derivative, it's got to be followed by that variable, that variable over dt. So this is going to be 2x dx dt plus 2y dy dt. It's going to be equal to 2s ds dt. That's the equation I want. Now, after I have the equation I want, I can stuff all those numbers in. Okay, so now let's look at the numbers. What I know is I know that the police cruiser is 6 miles north, so I know y is equal to 0.6. So now, remember that now at this moment we can plug all these numbers in, okay? So what I know, knowns, is that y is equal to 0.6. The car is 0.8 miles east, so I know x is equal to 0.8. So that takes care of that one, that takes care of that one. The police determined that the distance between them and the car is increasing by 20. So this is the distance, so I know s. Well, actually, it says that the distance between the car is increasing by 20. So is that s? Well, if something's increasing, that's a rate of change, right? So actually, when it says it's increasing by 20, that means it's getting 20 and it's going to be positive. All right, let's see some other things. So if the cruiser is moving at 60 miles per hour at the moment, now remember the police cruiser is moving down. So since it's moving down, is y getting bigger or smaller? Yeah, y is getting smaller. So that means that this dy dt is actually negative because y is changing. Y is getting smaller. So actually, so this should be negative 60 because that's the speed of the car. And I don't know, dx dt is what they're asking, right? They want to know what is the speed of the car. Well, I need to know dx dt, so I don't know that. So there's two unknowns that we can't figure out so far. I don't know s and I don't know dx dt. Well, we can find s using this equation. The original equation relates the sides to each other. So with these, I know I can find s. So what I know is s is going to be equal to the square root, so just solving for s, of x squared plus y squared. So this is going to be 0.8 squared plus 0.6 squared. So I think it's just 1. This is 0.64, this is 0.36. Yeah, it should just be 1. Yep. So this is going to be equal to 1. There we go. Now this is our question mark. This is what they're asking for. So now that I know all these variables, I can use this one to figure that out, okay? So what I'm going to do, I'm going to plug them all in, and then I'm going to go and solve for dx dt. So 2 times x, which is 0.8 dx dt, so using this equation with all those constants, plus 2 times y is equal to 0.6, dy dt is negative 60, is equal to 2 times, I guess I could have canceled all the 2's. Maybe we'll do that in a little bit. 2 times S, which is equal to 1 times dsdt. dsdt is 20. Okay, the first thing we can do is we can cancel 2, right? Divide everything by 2. Now we can simplify this. So this is negative 60 times 2 is going to be times 0.6. So this is negative 36. So 0.8 dx dt, let's go up here, minus 36 equals 40. So adding this, I'm going to have 76. 76 divided by 0.8 is going to get bigger. It's 95. So dx dt. Wow, are they doing 95? I'm messing up. Make sure to screw that up. Make sure I didn't mess any of this up. Y is equal to 0.6. X is equal to 0.8. This is equal to 1. Okay. 0.8 dx dt. 0.6 dy dt. 2 times 4. I think we're good here. Yeah, I think I might. The car's flying. I want to double check the math here, so. Yeah, that's right. But I only have 20. Oh, that's why. I found it. 2 times 2, this is 20. That's what it is. So this is 56. Divided by 0.8 is going to be equal to 70 miles per hour. Okay, so they're speeding. All right, so so that's kind of the idea that you can find that. So what's kind of interesting is if somebody's clocking you on a different road while moving, the math is quite complicated. The only number they're getting is actually this distance here. So if they know this, I would almost ask them, if they say you're speeding, I'd almost ask them to see the math. All right, last example of this. Filling. So water runs into a conical tank. You should still have salsa in it if you want it. A conical tank at a rate of 9 feet cubed per minute. So remember, you're filling something, so it's a volume here. That's why it's cubed. The tank stands point down and has a height of 10 and a base of 5 feet. How fast they are is the water rising when the water is 6 feet deep. Okay, so again, we're going to just show a picture here. Try not to scare you guys real fast because the whole idea is come up with a relating equation and then take its derivatives. Kind of knowing what are constants and what are not constants is really kind of the idea here. So what I'm going to do is I'm going to draw myself this conical shaped, basically like a coffee filter, what this looks like. So something like this. That's right. So what we know is we know that the height of this cone right now is 10 feet. And we're going to be filling water up into here. I'm not sure. And then we know that the radius of this thing is 5 feet. I don't like putting numbers in there right now, to be honest. I think those are misleading, to be honest. Let me get rid of those. They're hyper misleading. Okay, so I don't like that anymore. Okay, what I know is I'm filling this up with water. So we have some water here that we're filling up. So the things that I need to know is notice that when you're filling up this water, that this water itself makes its own cone. So what I need to do is I need to figure out the volume of just this cone right here. I just need to find the volume of basically this thing right here, because this makes a cone. Now, think about it this way. When you're filling up water, a whole bunch of stuff is changing. A bunch of stuff is changing. So let's just figure out what's the volume of a cone. Because that's what they're asking you to do. They're like, how fast is the water? Well, let's see. Let's make sure. The tank stands at a point as a height of, how fast is the water rising when the water is 6 feet deep? Okay, so they're giving you a rate of change of the volume, so that's why we know that we have to go volume to radius. So for a cone, I know volume is equal to 1/3 pi r squared h. I will give you the formulas. I'm not expecting you guys to memorize these things. So right now, just kind of Google them. But I will, I'll give you a formula, or to be honest, I'm going to give you something that you should know already. So the Pythagorean theorem, I'm not giving the Pythagorean theorem. That's something that should be burned in your brain by now. All right, so let's see what's changing. Well, if this water is going up, the radius right here is going to be changing. So this right here is going to be our r. This is r. And this right here is our height, which is also changing. So since all these things are changing, and this is changing as well, none of these things are constants. So we have to take the derivative with respect to t of both sides. So a v, and I'm going to pull out the constant, because I know we can do that. This is going to be the derivative with respect to t of r squared h. Now, things that we have to be careful of is, remember, r and h are both variables. Since they're both variables, you have to treat them as two different functions. So, this is going to be essentially your f and your g. So since it's a product of f and g, you're going to have to do f prime g plus f g prime. So this side is going to be dv dt, and this is going to be 1/3 pi times, well, the derivative of the first times the second plus the first times the derivative of the second. So there you got it. Okay. All right. So in order to find these things, what we have to do is we're going to have to plug in all these values. Let's see what things that I know. Anything else? Let me see.
Try.
No, just
It's right.
That's right. I just want to make sure, because this doesn't look right. But the heck with that. This is what we're gonna do. Okay, so let's make sure that we have all our variables. So this 10 and this 5, I'm almost certain is going to come in somewhere. Trying to see exactly why that's the case. What I see is I see some similar triangles here, like just for some reason, this is glaring at me, and I want to make sure that this is right. So what I know is that if you're just looking at this part of the triangle, that this is 5 and this is 10, and what we have is we have a water of, oh, I see. This is R and this is H. The reason why we can do this is I don't think it gives us all these letters, so what we have to do is we have to relate them all to something. So what I know is that, let's make sure. So if I try to fill this up, I know that the rate of change is equal to 9. So I know that this piece right here is 9, right? So that's 9. This is 1/3 pi. The radius, it doesn't tell us the radius. So I don't know what R is. But it says the height is equal to, yeah, the height is equal to 6. So this is 2 times, I don't know, times 6 plus, I don't know, squared, times, the change in the height. How fast is the height changing? Well, that's what they're asking us. Yes. So we have to find R. Well, what I know is at this particular instance that H is equal to 6, so I can find that R. Since these things are similar triangles, 5 over 10 is going to be equal to R over 6. So 30 over 10 is equal to R, so 3 is equal to R. So we can pop 3 in these locations. And now the only unknown is that DHTT, so we can go ahead and find it. So 9 is going to be equal to 1/3 pi times 6 times 6, which is 36, plus 9 DHTT. So 27 over pi is going to be equal to 36 plus 9 DHTT, divided by 36, so 27 over 36 pi is going to be equal to 9 DHTT. And finally, divided by 9, so 9 goes into 27 3 times, and 3 goes into 36 12 times. So this is 1 over 12 pi is equal to DHTT. All right. And that's that. You guys are going to have a lot of questions on this. This is something that the students fight with. The thing is find your relating equation, take its derivative. Be careful if anything's a constant. Okay, be careful of constants. None of these things are constants because everything is moving. So it's important that you look at what's moving so you can figure out what things are constants. Because if they're not constants, you have to take the derivative. If they are, you can just put in the constant, and then you don't. Or if it is there, depending on the derivative, sometimes it's 0. So just have to be a little careful. All right.